Our solar system feels incredibly stable, doesn't it? Earth going around day and night, the moon doing its thing, sun always there. It feels, well, permanent.
Uh-huh. On the surface, absolutely. It seems like clockwork.
But that's the fascinating part, right? That stability, especially when you're just looking at it over a human lifetime, it's maybe a bit of an illusion.
It can be, yeah. Because underneath, everything's constantly moving, pulling on everything else. It's this incredibly dynamic dance.
And that balance, that seemingly perfect clockwork, it can get disrupted. Profoundly sometimes.
Exactly.
So that brings us to our core question for you today in this deep dive. Could stars, passing stars, have actually messed with Earth's orbit way back when, enough to trigger, say, huge climate shifts in the distant past?
And that's where we're headed. We're going to dig into some new research that tackles exactly that. It's really about using these powerful scientific models to understand things happening over, well, just immense timescales. Millions of years, stuff we can't possibly see directly.
Right, stretching way beyond our own experience. And specifically, we're focusing on a new paper. It's coming out in the Astrophysical Journal, and it's titled No Influence of Passing Stars on Paleoclimate Reconstructions Over the Past 56 Million Years. That's by Richard Zeeby and David Hernandez.
Yeah, quite a definitive title.
It is. So our mission today for you listening is to unpack what that actually means and why it's kind of shaking up some previous ideas about Earth's history.
Okay.
Maybe we should start with the basics, though. What exactly is a stellar flyby in this context?
Right. So put simply, it's just when another star, one not part of our solar system, passes close enough.
Close enough to do what exactly?
Close enough for its gravity to cause some kind of disruption. A gravitational nudge, basically.
Okay. And does this happen often? Our neighborhood seems pretty empty.
Well, yeah, our little corner of the Milky Way is relatively sparse compared to, say, the galactic center. So they're not happening every day, but they definitely do occur over long time scales. They're not unheard of.
And we actually have a fairly recent example, don't we? Schultz's star.
That's a great example, yeah. About 70,000 years ago, which is, practically yesterday in cosmic terms.
Right.
It passed right through the Oort cloud.
And the Oort cloud is that really distant shell of icy stuff, comets way out beyond the planet.
Exactly. Our solar system's deep freeze, you could call it, full of long-period comets and planetesimals.
So Schultz's star went through there. Did it cause any trouble?
Well, it might have perturbed some comets, knocked them off their usual paths. But here's the thing. Even if it did, it would take maybe a couple of million years for any of those disturbed comets to actually make their way into the inner solar system where we are.
Ah, okay, so it's a long fuse.
A very long fuse. But even besides potentially sending comets our way eventually, these flybys, as Zeeby and Hernandez mentioned, can have other, maybe more subtle effects.
Like what?
Things like influencing the solar system's long-term dynamical evolution, how the planet's orbits might change over millions, even billions of years, and maybe tweaking the properties of those objects out beyond Neptune, the trans-Neptunian objects.
So scientists have been wondering, could these flybys, these gravitational nudges, maybe subtly alter Earth's orbit enough to affect our climate way back in the past?
Precisely. That's been a question lurking for a while.
Which leads us perfectly to this big climate mystery. The PTM. The Paleocene-Eocene Thermal Maximum.
Right, the PTM. This happened around 56 million years ago, and it really stands out in Earth's climate record. It's what scientists call a hyperthermal episode.
Hyperthermal meaning really hot, really fast.
Essentially, yes.
Yeah.
We're talking about a global temperature jump of 5 to 8 degrees Celsius.
Wow, that's 9 to 14 degrees Fahrenheit. That's enormous.
It is enormous, and it happened alongside this massive injection of carbon into the atmosphere and oceans. We're still figuring out exactly where all that carbon came from.
And the timescale for this, it wasn't overnight, presumably?
No, but geologically speaking, it was pretty quick. The temperature rise itself might have taken something like 10,000 or 20,000 years.
Okay.
And the whole warmer period lasted for maybe 100,000 or 200,000 years before things started to cool back down.
And the impact on life, the sources say it was massive.
Oh, absolutely. Lots of marine organisms, particularly those living on the seafloor, went extinct. On land, tropical and subtropical zones pushed much further toward the poles. And interestingly, this is right around the time we see the first appearance of primates and some other modern mammal groups in the fossil record.
So a really pivotal moment in Earth's history, but the cause is still debated.
Still debated, yeah. There are several leading ideas. Huge volcanic eruptions pumping out CO2, maybe a massive comet impact, the sudden release of methane from methane, clathrates, those icy cages of methane on the seabed,
Right.
or changes in Earth's orbit, what we call orbital forcing.
Okay.
But crucially for our chat today, it was also suggested not too long ago that maybe passing stars were a driver for paleoclimate changes around this time.
Ah, connecting the flybys to the PTM.
Exactly, including potentially the PTM itself.
Okay, so how would that work? What's a proposed mechanism for a distant star messing with Earth's climate?
Well, the thinking was that it's not necessarily the star directly affecting Earth's orbit by a huge amount. The star's gravity is pretty weak by the time it gets here.
Right.
But the idea was that the giant planets, Jupiter, Saturn, Uranus, Neptune, with their huge gravitational fields, could act as amplifiers.
Amplifiers. How?
The passing star gives the giant planets a little gravitational nudge, and because they're so massive, that nudge gets magnified and passed along through the complex gravitational interactions within the solar system.
Okay.
And eventually, that could subtly alter the orbits of the inner rocky planets like Earth, maybe change our tilt or the shape of our orbit, just enough to trigger a climate shift like the PTM.
That actually sounds plausible, like a cosmic domino effect.
It did seem plausible, and it tied into research published just last year by Nathan Kaib and Sean Raymond.
Right. What did their work suggest?
Their simulations, based on their models, did find that these close-passing stars could significantly alter the orbital evolution of the entire planetary system. They specifically perturbed the giant planets, and they concluded, and I'm quoting here, that the long-term orbital evolution of the Earth and the rest of the planets is linked to these stars.
Okay, so their work pointed towards, yes, passing stars could be a factor, potentially explaining things like the PTM.
That was the implication, yes.
Which makes this new paper by Zeeby and Hernandez even more striking, because they look at essentially the same question and come to the completely opposite conclusion.
Exactly. They state it very clearly. In contrast to Kaib and Raymond, we find no influence of passing stars on paleoclimate reconstructions over the past 56 years.
So wow, same puzzle, different answers. How does that happen in science? What's the difference here?
Well, it really seems to boil down to the completeness of the scientific models being used.
Completeness.
Meaning how many factors, how many physical effects you include in your simulation. You see, running these incredibly detailed, state-of-the-art solar system models, especially over millions or billions of years, it's just massively computationally expensive. It takes huge amounts of computer time.
Okay, so researchers sometimes have to simplify things.
They often do, yeah, to make the calculations feasible. So many previous long-term studies, especially looking way, way back, might have used simplified models.
Yeah.
Maybe they only focus on the outer planets. Or, crucially, sometimes they even left out the moon.
They left out the moon. Isn't that kind of important for Earth?
You'd think so. And that seems to be the key difference here. Zeeby and Hernandez use what they call a state-of-the-art solar system model.
And crucially.
Crucially, their model included the moon's gravitational pull, and it also included something called J2.
J2, what's that?
It's basically accounting for the fact that the sun and moon aren't perfect spheres. They bulge slightly at their equators, and that slightly non-spherical shape affects their gravitational field in a subtle but measurable way. It's called the quadrupole moment.
Okay, so they included the moon and this J2 effect. More detail.
A lot more detail.
Yeah.
And they ran a huge number of simulations, 400 different setups with random stellar parameters covering about 1,800 different stellar flybys in total.
And what did they find when they included these extra factors?
This is the fascinating part. They found the moon has a profound stabilizing effect on Earth's orbit.
Stabilizing? How?
It seems the moon's gravity helps to damp down or resist some of the subtle perturbations that might otherwise accumulate over long periods, including those potentially caused by passing stars via the giant planets.
So models that don't include the moon are missing this crucial stabilizer.
That's exactly what Zeeby and Hernandez argue. They say models, excluding the moon, reach suspect conclusions. In their more complete model, even flybys that were extremely close, ones you'd intuitively think must have had an impact,
Yeah.
they seem to have basically no significant effect on Earth's orbital evolution in a way that would line up with triggering major paleoclimate shifts like the PTM.
Wow, so the moon is like our orbital bodyguard.
Kind of. It underlines their main conclusion. Our results indicate that a complete physics model is essential to accurately study the effects of stellar flybys on Earth's orbital evolution.
It really highlights how leaving out even seemingly small details in these huge cosmic simulations can lead you down the wrong path.
Absolutely. Those computational shortcuts, while sometimes necessary, can mask crucial physics.
Okay, so this new research strongly suggests passing stars weren't the trigger for the PTM 56 million years ago. But the universe keeps moving, right? There have been lots of flybys, and there will be more.
Oh, definitely. The cosmic traffic continues.
And there's one future flyby people talk about, isn't there? Gliese 710.
That's right. Gliese 710, it's an orange dwarf star. And current projections suggest it's going to come pretty close.
How close is close?
Expected to pass within about 0.1663 light years, which sounds like a lot, but in stellar terms, it's nearby. That's about 10,500 astronomical units, or 10,500 times the Earth-Sun distance.
Okay. And when is this happening?
The estimate is in about 1.29 million years from now. So not tomorrow, but geologically, it's on the horizon.
And the concern is?
Well, there's a pretty high chance, some studies say around 86%, that it'll pass directly through the Oort cloud.
Ah, back to the Oort cloud. Like Schultz's star, but maybe closer or bigger.
Potentially, yeah. And the worry is that it could perturb a lot more comets this time, potentially sending a whole swarm towards the inner solar system later on.
So even with this new research showing the moon helps stabilize Earth's orbit against orbital shifts from flybys, does that mean a future flyby like Gliese 710 poses no threat? Could it still trigger climate change? Maybe through comet impacts?
That's still an open question, really. This new paper focuses on the subtle, long-term gravitational effects on Earth's orbit. It doesn't necessarily rule out other consequences, like an increased influx of comets caused by perturbing the Oort cloud.
Right. Different mechanism, potentially different outcome.
Exactly. So understanding the full impact, past and future, of these stellar encounters still depends heavily on refining our models, making them as complete and accurate as possible. It's an ongoing process.
It really feels like the big takeaway here is about the models themselves.
I think it's absolutely right. The central finding really underscores the power and the necessity of using complete scientific models. It's not just about plugging in data. It's about making sure you've got all the relevant physics, all the important components interacting in the right way, especially for something as complex as the solar system over millions of years.
So for you listening, what we've deep dived into here is pretty fascinating. This huge ancient warming event on Earth, the PTM, might not have been caused by a passing star, even though that was a compelling idea, and the surprising hero in this story, our own moon, acting as an orbital stabilizer, something that less complete models apparently missed.
Yeah, the moon plays a bigger role than maybe we give it credit for sometimes.
So what does this all mean for us? Well, while the deep past might be a bit less influenced by stellar drive-bys than we thought, the future, as we saw with Gliese 710, still holds its own cosmic close calls.
That's true.
And this deep dive really shows that sometimes the biggest discoveries aren't about finding out what did happen, but about getting a much clearer picture of the full complexity of why things happen, or maybe why they don't happen in this incredible cosmic dance.
Well said.
It really makes you wonder, doesn't it? What other assumptions that we hold about Earth's long history, or even the solar system's future, might just be waiting for a more complete model, a model with all the pieces included to finally reveal the deeper truth? Our solar system feels incredibly stable, doesn't it? You know, Earth going around